Hello, today we are going to open a new series on AQA AS level physics revision. Today's topic that we are going to focus on is thermal, one of the topics in the end of the AS spec, which should be kind of familiar to you if you are watching it on some similar time as me in 2025 in the beginning of May. So let's start. So the first part that we need to know about thermal physics is something about things that we may have already learned before in GCSE. So let's just move on. First thing that we need to know is the things about moles, temperature, on something about internal energy. I'm just going to call it IE, and also something like some basic formulas of all of those things. So let's just check it out. So firstly, what we have is mole. The mole. Note that it is one of the SL units. It is a measure of amount of substance, the quantity of the thing. So the way that we define a mole is that a mole is equal to quantity of substance that contains Avogadro constant number of particles. So you can also say that like quantity of substance that contains 6.02 times 10 to the power of 23, which is like the value of it. We need to remember this amount of particles. So here's about moles, pretty simple, and we may have already seen it before somewhere else, maybe in GCSE chemistry. And then we're going to move on to the second part. The second part that we are going to focus on is also something that we have learned before. Which is something about mass. Mass equals the number of moles times by the molar mass. This small n stands for number of moles. We will also face like a capital letter N, which stands for the number of particles. The calculation of it would simply just be capital N equals N times by Na. Na is Avogadro's constant. 6.02 times 10 to the power of 23. And we also need to know about the particle model. It's also something that we've already learned before. So basically we know the things about solid, liquid, and gas. I'm not going to write it on the board. Just remind yourself about the arrangement of particles, how in a solid state, particles are closely together and arranged in a regular pattern. Like for example, like this. But in a liquid, although they are still close together, they are arranged with no pattern. Imagine random arrangements. Like they're so close together, but they can exist like in random arrangements. However, in gas, they are far apart. There are rarely any connections between different particles in the gaseous state. And it's also random arrangement as well. For the movements of particles, we have the solid ones. They are only restricted to their position. They can only move like by vibrating, or like basically they're just vibrating apart with no movement, vibrate on the spot. And liquid, they move around each other freely, and gas, they move quickly in all directions. So you can probably see this thing moving there, this thing moving there, that thing is there, this is over there, something like that. And so this is about those three states. And let's move on. The next thing that we are going to talk about is a thing that's pretty confusing. Here is a word. It's HEAT, heat. What does it mean? I mean, in physics, in thermophysics, we actually say that it's a verb and it stands for the transfer of energy. The transfer of thermal energy, I mean. So the thing is that it's actually an action we do on things. Heat is not equal to thermal energy, or the state of being hot. And temperature is also something that we need to remember. There's definitely like a definition question somewhere, or something that uses this definition. It's basically the measure of the kinetic energy of the particles. The measure of the average kinetic energy of the particles, if you like. Even better if you say random KE. But that's something for internal energy afterwards. And what we also have is some other things as well in this subtopic, things that we need to remember, try to get some memories back to our mind, is set the temperature scales. We have Celsius, also we have Kelvin. A Kelvin is the same size as 1 degree Celsius, but the Kelvin scale starts from the absolute zero. The way that we convert one from the other. If you want to calculate centimeters from Kelvin, we just basically decrease the value of the Kelvin by 233. If you want to calculate Kelvin, you just add 233, 73 from its value in degrees Celsius, which is pretty simple as well. And then we are going to meet another definition, something about what does absolute zero mean. So the things about it is when the particles don't move at all, or you can say it in another way, the least, like the lowest possible temperature that you may have. But we can also explain it in other aspects as well. Like as I said before, in a solid state, particles, they have regular patterns and they can have like vibrations on its points. At absolute zero, nothing is moving. So you can say that the particles within the substance is not vibrating at all, as well as another alternative definition, something that you can write, but probably not in an exam. Because for definition questions, those things are really weird. Sometimes they just give marks, sometimes they don't give marks. So then, it's something about internal energy. This is another concept that we need to know. Internal energy is like the sum of random kinetic energy. Or we may say it in another words, thermal energy. And also, what do we have? We have also potential energy. Note that in ideal gas, potential energy is zero, so you can ignore it. So here's our internal energy. And let me just check, are there anything else that we need to know in this pretty like small subtopic? I think that's everything. But oh yeah, we do need to know something else. We do need to know it. So the change of the internal energy of system is equal to the sum of the thermal energy added to the system and also the work done on it. Is presented by this equation. Delta U equals W plus Q. But since we have W equals P times by delta V, so we can also say that delta U equals P plus, Q plus P delta V. which this delta V is change in volume, that P is pressure. The work done equals pressure times by the change of volume. If you want to derive it, you can go search. There are plenty amount of resource for you to try to understand it. I'm not going to explore it further over here because it's just like a rough revision session to help you to go through all of the topics and go check what else you can still revise on and something like that. So here's like some pretty simple stuffs, and then we need to know something else. We need to know about several laws, the ideal gas laws. So the first one is Boyle's law, and the second one is Charles' law. The third one it's called the pressure law, which seems a bit weird comparing to the else two. The empirical gas laws. Sorry about my writing. It's always bad. So the first one that we have is Boyle's law. The equation of it is P1V1 equals P2V2, or you can write it in another form. P1 PV equals constant. You do need to have some other things to apply it, which is you need to have a fixed mass of gas and constant. And also you need the fixed temperature as well, so you need to add a T as well. This T, the capital letter T stands for temperature, lowercase stands for time usually. And we also have Charles' law. We have V over T as constant. Or you can say V1 over T1 is constant, which also needs the mass to be constant, and also we need the pressure to be constant in this case. And the third law that we need to know is the pressure law. For the pressure law, we will need P over T is constant. Pressure over temperature is constant if we have the mass is constant, and also we have the volume is constant. So those are the three empirical gas laws. By the way, I think we also need to know about something about empirical laws and also theories. So empirical laws, they come from experiments, and they basically how we find patterns of experiment data. So you can use it to predict, but we cannot use it to explain. And for theories, they comes from assumptions and also the logical approach to prove something. So we're able to use it to predict as well as explaining what's going on within the system. And we are about to know like one of those theories afterwards. It's called the kinetic theories, also in this thing. And together we find like those equations, they have something that we can combine them together to form like an overall equation for those things, which is after something, if the mass doesn't change, P1 V1 over T1 equals P2 V2 over T2. This is like an ideal gas law that we will generally use. Personally, I don't know why we still need to divide those things up into three of them, which is kind of a bit weird. This is the ideal gas equation. And we also need to know something else as well. The thing that this part, the P1V1 over T1, it stands for something else. It stands for constant times by the number of particles. As I say, if the mass doesn't change, if the number of particles doesn't change, this thing just holds. So it's definitely constant times by the number of particles, shouldn't it? So which thing is it? It's basically if you're measuring in number of moles, then we have R, which is roughly like 8.31. If we are measuring in number of particles directly, then we are timing by K, which is another constant, roughly 1.38 times 10 to the power of minus 27, minus 93, I mean. Which if you want to give them like a unit, it would be joules per Kelvin. So combine these things together. We may have P1 or just PV something. PV over T. Let me just check whether can you guys see it or not. Oh no, it's being covered. Okay, so let's just move to the other side of the board and write it again. We have PV over T equals NK, or we can rearrange it and find like a better form of it, NKT. This capital letter N stands for the number of particles, as I previously mentioned. This K is a constant, this T is the temperature. Also, you can write it in the other form, where the lowercase n stands for number of moles, and we also have RT, which R is the constant, roughly 8.31, and T is the temperature. Those are the equations that we normally and frequently used in those questions. And we also need to know something about ideal gas. We do have some like assumptions on it. So one of the assumptions that we have about our ideal gas is we say that it has no potential energy, as we have already mentioned somewhere else. So basically no potential energy stands for there are no bonds between those things. There are no interactions between those air particles. And then we need to talk about something else. The kinetic theory. This is a hard topic. The way that we derive some of the formulas, it won't be so easy to just derive it over here in like 5 minutes. So I'm just going to write down the equations that we have. We have PV equals a third NM CRMS squared. So which this P stands for pressure and this V is volume. This a third is just a third. This N is number of particles, but this M, by the way, we need to know that this M over here is mass of one particle. It is not the mass of the whole object, it's just one particle, so we need to just have a remind on this thing. And N times by M is just basically the mass of the overall thing, obviously. And CRMS. The RMS here stands for root mean squared. So it's not like the usual average velocity, it's something else. And since we also have PV equals, I'm not going to use red pen for this thing, it's not that important. Since we also have PV equals NKT, we can also say that those things are equal, those two equations. We can also write an equal sign on those sides as well. So yeah, so based on this, we can get another formula, which is 3 over 2, K equals 3/2 times by kT. This is like the kinetic energy of it. The kinetic energy of the thing. And also we can also say that this KE, wait, let me just check. Is it can you see it or we can't? And just move a bit to here. So by the way, this K we can also write it in another form, half V this it's actually half mv squared, but here the V we just use CRMS instead. Half CRMS squared equals 3/2 kT. In another way, this is another thing that's pretty important that we are going to use frequently in our exams, in our questions. So those are basically the things about kinetic theory. And then we're going to introduce another thing called Brownian motion. So first, here are the things that we need to know. So if we have like a bunch of air, it's going to be full of different particles, you know? So and those particles are moving randomly and in very quick, very fast velocity, very large velocity in all directions. So she plays some small particles that we can observe, but not that small, so we can observe. With the collisions of the air particles inside, it's going to have a kind of a zigzaggy random motion, which is called the Brownian motion. What this proves is that the air actually has so many kind of air particles, which firstly, they are small in size, so you can't see it. And also, they must be small in mass as well. Uh, and also, because that it can still cause like an observable effect on like the smoke particles that we release into the air, we can know that they have high Ke to be transferred or onto the particle, onto the smoke particle. Therefore, we can infer that it has a great velocity, a high speed. And also, because the motion is random, it's going to zigzag in like random directions. So we can also infer that those air particles, they are moving in random direction as well. Which those are the facts, the things that we can conclude from here, from this. And we also have some assumptions for the kinetic theory as well. As I said, this is a theory. So firstly, we are going to have we are going to assume that air particles, they are small solid spheres. Well, to decrease the time, I may not write the whole version of it afterwards. And also, it has the thing of some of the properties of those air particles. We assume them to be totally inelastic. So if we have learned mechanics, we will know that the E should be 1 within the collisions. And also, we are going to assume that the time of the collisions of those particles onto the wall of its container is negligible comparing to the time which it travels between the walls. And here is another assumption. And we are also going to assume other things as well for this air particle. We are going to assume that a large number of air particles is within the container and they are traveling in random directions with random velocities, but we going yeah, but those things are the thing as well. So those things everything about kinetic theories. And basically, this is it. And then I'm going to give you some questions and I'll leave some time for you to think and then I'll say the answer out. The first question is, what is the lowest possible temperature an object can theoretically really reach cold? The answer is absolute zero. I think I'm going to leave this question part in another part of it. Okay, I'm going to write the answers down over here. First question, the answer is absolute zero. And which is quite easy. The second question, what is the value of these temperatures in Kelvin and degrees? Oh, I think I forget to say it. Just have a think. If you know the value, just say it out loud and then just drag the video to the place which I released it, which I say what the mark scheme is. So basically, it's going to be 0 kelvins or negative or minus 273 degrees Celsius. If you want to be precise, you can add a 0.15 over there, but it doesn't matter really. And the third question is that we're going to have, what is meant by the internal energy of a body? Internal energy. Okay, so the answer is, it is the sum of the randomly distributed kinetic and potential energy of all of its particles. So we can just remember random KE plus potential. And the fourth question. Oh my god, what am I preparing? Why did I prepare a sketch question? A sketch graph to show that the speed distribution of molecules of gas at 100k and 250k. I don't remember where to find it. Let's just skip it. So, question 4. State 2 ways in which increasing the temperature of gas affects the speed of the gas molecule. How does increasing the temperature affect the speed? So basically, the temperature increasing it means the average speed increases. The average molecule speed increase. Or in terms of the graph, we are going to see the distribution of molecule speeds becomes out. So it's basically like if we have this is the original, we are going to have this afterwards. If we increase the temperature, which here is the proportion. This is the proportion. I'm going to call it P temperately, and here's the speed. I'm going to call it S temperately. Means that this is not really a proper symbol for all of those quantities, for all of those things. And then another question. What is specific latent heat of fusion? The specific latent heat of fusion is basically the quantity of thermal energy needed to transfer to melt or freeze 1 kg of a substance. Oh, I just realized this is something that I forgot to cover. Also, something about specific heat capacity as well. It's basically the amount of energy required to heat 1 kilogram of substance by 1 degree centigrade or 1 Kelvin if you like. And then let's move on to the next topic. Gas laws. Okay, the first question is, what must be true of a gas's mass for it to obey the three gas laws? As we already know, possibly it's needed to be fixed and constant. And then the second question, what is Boyle's law? So Boyle's law is basically, it states that at a constant temperature, the pressure and volume are inversely proportional if the max is fixed. Basically, we just say what PV equals constant means, like we say it in words. And then another question, what is Charles' law? So Charles' law, it states at constant pressure, the volume V of an ideal gas is directly proportional to its absolute temperature T. And also, what is the pressure law? As another question. The answer is the pressure law states that at constant volume, the pressure P of an ideal gas is directly proportional to its absolute temperature T. Note that all of the temperature is absolute temperature, so we are going to measure it in Kelvin instead of degrees centigrade. Why is my C looks like a circle? So those are the things that we need to mind. And then we can move on to some ideal gas equation questions, which are basically the hardest. What is the relative molar mass of a substance? Oh, I guess that's quite easy. Oh, so basically the relative molar mass is the sum of the relative atomic masses of all of the atoms that make up the single molecule. So here's something that we need to mind of. The thing is that within the exams, we may need to face different molecules instead of the atoms. So when we saw hydrogen gas, we need to know that it stands for H2 rather than just one H itself. Its relatively molecular mass would be 2 instead of 1. So then we move on to the next question. What is Avogadro's constant? So I haven't talked about that, but it is defined by the number of atoms in exactly 12 grams of carbon isotopes, 12, C12. Its value is 6.02 times 10 to the power of 23. So, another question? Write down the ideal gas equations for n moles and state what each term represents. So, since we are going to write down the ideal gas equations based on moles, we are going to use the smaller case n with the constant r. So here is the equation. P stands for pressure, and V stands for volume. The n stands for number of moles. The r stands for the molar gas constant, which is 8.31 joules per mole per Kelvin. And also T is the temperature. Kelvin, remember again. So when we are doing thermal, we are for all of the equations, or like most of the equations, we are going to use kelvins instead of degrees centigrade. But they're basically the same. Just watch out for the 271, the conversion between the units. And then, right, what is like the highest? Nah, that's not a good question. Sometimes I just find like the questions are prepared are not good enough. So write down the equation for work done when the changing volume of gas at fixed when changing volume of gas at fixed pressure, and state what each term represents. So basically, we have work done equals P delta V. The work done equals pressure times by the change in volume. If you want to derive it, it's actually pretty easy. We will know that the work done is equals to force times by the distance. And we know that force equals pressure times by the area times by the distance. If you have like a cylindrical object, the area times by the distance is just its volume. And since it is the volume that's changed, the d is the change of it, we are going to write delta v, which delta stands for change in something. And then we are going to move on to questions of other topics. Kinetic theory. I find my writing and spelling are not good enough. So the first question is, what does CRMS represents? So basically, it is the root mean squared speed of the molecules in the gas. So we can write it in like this form, like this. The root mean squared speed. So it's technically not the same as the average speed or velocity. So yeah, here's the thing. And then the second question. Give two reasons why increasing the temperature of gas increases the force it exerts on the wall of its container. So this question is pretty open. We can talk about it from many perspectives. So first we can say that the average change of momentum is within one collision is increased and the average time between the collisions is decreased. This results that the rate of change of momentum is greater and the force on the wall is increased. We can also say in other aspects as well, but this is like the best one that we can talk about. And then states four assumptions made about an ideal gas in kinetic theory. So the first one, we have all molecules are identical, so to forget to mention about it before. And we also have the gas contains a large number of those molecules. And also the molecules have negligible volume compared with the volume of the container. The molecules continually move about randomly. And also the collisions between the molecules or at the wall of the container are perfectly elastic. Molecules move in a straight line between collisions. And also the forces that act during collisions last for much less time than the time between collisions. Or we say in the negligible instead. And then explain using kinetic theory why we increase the temperature of a fixed mass of gas in a container must lead an increase in its volume or pressure. So increase the temperature, fixed mass of gas must lead to an increase in its volume or temperature. So I just realized the mark scheme I have is not the same as the mark scheme that should be on this question. So the thing is, when we increase the temperature, we increase the average Ke. The equation that we have is PV equals a third nm CRMS squared. Since we increase the temperature, the value of CRMS is going to increase as well. Since we have a fixed mass, so N and M are not going to be changed. And since the third is a constant, it's going to lead an increase on the left hand side. So either volume should be increased, or the pressure should be increased, or they both increase, or one of them decrease and the other one increase. This is the result that we can get based on the equations that we have. And then, also we have some other questions as well. For an ideal gas, what can you assume about the internal energy? This is something I've already talked about. So basically, we can assume that for the all of the internal energy is in the form of the kinetic energy, because potential energy is 0. And okay, another question. Give an example of both a theoretical and empirical concept, and explain the difference between the two. So the answer would be pretty straightforward and simple. Theoretical concepts, we can just talk about the kinetic theory. They are based on the assumptions and derivations from knowledge. They explain why something happens, like they assume what does one molecule does and apply it to loads of molecules within the system, and then figure out like an equation for them. However, uh, the empirical concepts, they are based on experiments and the results that we have. So they are based on observations and they can predict what happens, but they do not explain why they does. For example, the ideal gas laws that we have, Boyle's law, the ideal gas equation that summarize all of the three things. We know that those things are proportional, or something. If something is fixed, then the other two should be in constant. Something times by something is constant if the max is fixed and some other thing is fixed as well. However, we don't know how does it work. We only know that it does happen. So it is useful for predictions, but we cannot explain using those empirical laws. So this is basically everything in this video. See you next time, and tell me if you have like a nice results within the actual exam. Thank you for watching, and if you have any advice, please point it out in the comments section. Thank you.